Before we begin breaking down each section of this system, it is important to understand what you are actually looking at. This entire visual represents a hydrogen fuel cell ecosystem, not just a single device. Every section connects to another part of the process, and together they form a complete energy conversion system capable of turning hydrogen into electricity, heat, and water. At the center of the system is the fuel cell itself. Hydrogen enters from one side, oxygen enters from the other side. Inside the fuel cell, electrochemical reactions separate electrons from hydrogen atoms, forcing those electrons to travel through an external circuit where electricity is created. The remaining hydrogen protons move through a specialized membrane and eventually recombine with oxygen and electrons to form water. That is the core principle behind hydrogen fuel cells. But this system is far more complex than most people realize. A fuel cell is not simply a box that produces electricity. It depends on dozens of interconnected components working together simultaneously. The membrane must remain hydrated. Heat must be removed continuously. Air must be compressed and delivered at the correct pressure. Hydrogen must be stored safely and distributed precisely. Electrical current must be collected and converted into usable power. Sensors and safety systems must monitor everything in real time. That is why this visual is so important. It reveals the hidden engineering behind hydrogen fuel cell technology. Each numbered section represents a critical layer of the system. Some components manage chemistry. Others manage heat, airflow, moisture, electricity, pressure, or safety. If even one subsystem fails, overall performance and reliability can collapse. As we move through each section, you will begin to see that hydrogen fuel cells are not just electrochemical devices. They are fully integrated industrial systems combining chemistry, thermodynamics, fluid mechanics, materials science, electronics, and software control all at once. In this section, you are looking at the entry point of hydrogen into the fuel cell system. The blue hydrogen molecules shown near the upper left side move toward the dark catalyst surface in the center. As hydrogen reaches the catalyst, the molecules split into protons and electrons. The blue H+ symbols represent protons moving deeper into the system, while the yellow E symbols moving outward represent electrons leaving through an external circuit. This movement of electrons is electricity itself. What you are seeing here is the exact moment chemical energy begins transforming into electrical energy. Here you are looking at the opposite side of the fuel cell where oxygen enters the system. The green oxygen molecules flow downward toward the reaction surface. At the same time, protons arriving from the membrane combine with returning electrons and oxygen to form water and heat. The water molecules shown near the lower right side visualize the final product of the reaction. This section represents the completion of the electrochemical cycle that powers the fuel cell. This image shows one of the most important components inside the fuel cell, the proton exchange membrane. The large rectangular membrane in the center acts like a selective gatekeeper. Notice how only the blue proton symbols pass through the membrane while electrons remain blocked outside the structure. This separation is critical because it forces electrons to travel through an external circuit, generating usable electricity. The membrane must remain hydrated at all times to function properly, making water management a critical engineering challenge. This layered structure represents the catalyst layer where electrochemical reactions accelerate. The gold particles shown at the top represent platinum catalyst materials supported on a dark, conductive layer above the membrane. Platinum dramatically speeds up the hydrogen and oxygen reactions inside the fuel cell. Without this catalyst, the reactions would happen far too slowly to generate practical amounts of electricity. This section also highlights one of the largest industrial challenges in fuel cell technology: reducing platinum cost while maintaining durability and efficiency. This woven dark structure represents the gas diffusion layer. The arrows entering from above show hydrogen and oxygen spreading across the fuel cell surface, while the water droplet exiting below represents moisture removal. This layer performs several jobs simultaneously, distributing gases evenly, conducting electricity, supporting the catalyst layer, and removing excess water. Small flow imbalances in this area can create large efficiency losses across the entire fuel cell system. Here you are looking at the flow field plates that guide gases throughout the fuel cell. The metallic plate contains carefully designed internal channels that distribute hydrogen and oxygen evenly across the stack. These channels also help remove heat while collecting electrical current. This section represents the hidden circulation network inside the fuel cell system. The geometry of these channels directly affects efficiency, cooling performance, and pressure management. This large layered structure represents the fuel cell stack itself. Instead of relying on a single fuel cell, many individual cells are compressed together into one integrated unit to increase voltage and power output. Hydrogen enters from one side while oxygen enters from the opposite side. The lightning symbol above the stack represents electrical power generation. This section helps visualize how commercial fuel cell systems scale into usable industrial power platforms. This image focuses on how electricity leaves the fuel cell stack. The metallic edge plate gathers electrons produced during the electrochemical reactions and transfers electrical current into the external circuit. The yellow lightning symbol and outgoing electron arrow represent usable electrical energy flowing out of the system. Even small electrical losses in this area can significantly affect overall fuel cell efficiency. This section highlights one of the most underestimated components inside the fuel cell system: seals and gaskets. The black frame and metallic plate work together to maintain pressure while safely separating hydrogen and oxygen gases. Because hydrogen molecules are extremely small and highly diffusive, preventing leaks becomes a major engineering and safety challenge. Reliable sealing technology is critical for both efficiency and long-term durability. This radiator-like structure represents the cooling system responsible for removing heat from the fuel cell. The blue and red arrows show thermal fluid movement through the cooling loop. Fuel cells continuously generate heat during operation, and maintaining stable temperatures is essential for performance and durability. Without proper thermal management, components degrade faster and efficiency drops significantly. This cylindrical chamber represents the humidification system that controls moisture levels inside the fuel cell. The water droplets and airflow arrows illustrate how humidity is added into the gas stream. PEM fuel cells require carefully controlled hydration because the membrane only conducts protons efficiently when moisture levels remain balanced. Too little water increases resistance, while too much creates flooding inside the system. This turbine-like machine represents the air compressor or blower supplying oxygen into the fuel cell. Air enters from one side and compressed oxygen-rich airflow exits toward the cathode side of the system. This section demonstrates that fuel cells depend heavily on airflow management. Compressing air requires energy, meaning part of the electricity produced by the fuel cell is consumed internally to maintain operation. This image represents the hydrogen delivery infrastructure feeding the fuel cell. The green hydrogen storage tank, valves, regulators, and piping demonstrate that fuel cells rely on a complete pressure-controlled supply network. Hydrogen is typically stored at extremely high pressures, requiring specialized engineering systems to manage safe transport and delivery into the stack. This metallic control unit represents the power electronic system that manages electricity coming from the fuel cell. Fuel cells naturally produce DC electricity, but motors, batteries, and grids often require regulated and converted power. This section visualizes the converters, controllers, and electronic systems responsible for integrating the fuel cell into real-world applications. This final section represents the intelligence and protection layer behind the entire fuel cell platform. The digital display symbolizes continuous monitoring of temperature, pressure, voltage, gas flow, and system health. The shield icon represents operational safety and fault protection. Modern fuel cells are not just chemical devices, they are software-controlled industrial systems operating under constant real-time supervision.